Okay, sorry for being a little late, traffic, but it shouldn't bog me down in terms of time. Okay, so today is officially the last day of class before the review, so I'm going to finish up as much as I can. Well, this part of the course is probably the most interesting. It's unfortunate that I couldn't do a lab assignment on it, but I think it's something to cover anyway. That's pretty nice. Okay, so last but not least, we're going to cover a nice topic that you see often in the industry. It's called swarm intelligence. So think of programming little robots that are performing very simple tasks, and collectively they exhibit some sort of intelligent behavior, and they achieve a common goal. Okay? So we're going to cover two aspects of swarm intelligence. One is called particle swarm optimization, very well-known algorithm, and another one called ant colony optimization. So think of taking a problem and abstracting it into an ant colony and solving a common goal there. And then the second half will be a conclusion, just wrapping up everything that we've talked about, and some topics that I think are relevant in case you want to carry on your machine learning learning, take it to the next step. I've got a few topics that you might be interested in if you want to take your learning to the next level. Okay? And next week, I'll talk about the final exam structure. I'm still trying to figure out what exactly to ask. I'm not quite sure, but I'll finalize that by next week. And I'll do a final exam review. So any questions that are numerical in nature that are part of the problem sets, I'll cover those in class. Okay? All right, so swarm intelligence. What exactly is swarm intelligence? Well, it's very similar to genetic algorithms. Okay, so swarm intelligence and genetic algorithms, they consider a population of solutions, and you are using that population of solutions to try to find a minimum to your cost function that will provide a beneficial solution for you. Okay, so one thing is that it's very similar to genetic algorithms that we talked about last week. Okay, so swarm intelligence, or SI for short, and genetic algorithms, they create a population of solutions, or they create permutations of possible parameters, and then one of them will hopefully give you the desired minimum that you want. Population of solutions. Okay, that move throughout the solution space. So you have a bunch of initial solutions, and then what you want to do is you want to scan through the potential area of all possible solutions, and hopefully you'll land on something that will give you the best solution possible. It'll move through the solution space to search for what we call global maximum minima. So usually our cost function only has one unique minimum or maximum, and that's what we're going to assume for this part of the course. Okay? So swarm intelligence is an AI technique that is based on the study of collective or social behavior in decentralized, self-organized systems. Okay? So swarm intelligence is an artificial intelligence technique based on some big words coming, on the study of collective or social behavior in decentralized, self-organized systems. So, that's the official definition of swarm intelligence. Okay? So what I mean by decentralized is that there is no central control that each of these entities, report to. And self-organized means that they individually can learn on their own. So in swarm intelligence, you have individual units which are called agents, right? So for example, agents are just one unit out of the total collective. So lots of things, for example, there are some examples of swarm intelligence such as, ant colonies, bird flocking, fish herding, bacteria molding. All of them have individual agents that try to achieve a common goal. And one individual agent would be, an instance of that particular problem. Okay? So each one of them by themselves do very simple tasks that are considered non-intelligent. They basically go and do things by instinct. And collectively, altogether, they achieve a common goal, and they do exhibit some sort of intelligence. Okay? So, let me see, self-organized systems. So not terms, systems. Okay, so examples, common examples are, bird flocking, ant colonies. I'll define decentralized and self-organized in a little bit, but I just want to write these down. Bacteria molding, fish schooling, and so on and so forth. Okay, so I'm going to just define something. Some people, or in common biology textbooks, they refer to individual instances of bird flocking or ant colonies as an agent. Okay, so an agent is one of the scenario. Okay, so one ant, one bird, one fish, etc. Okay, so they're an individual part of the overall solution. Okay, so each agent in swarm intelligence is decentralized. So what I mean by decentralized is that there's no central commander, there's no leader that they refer to. They're completely on, if you leave them on their own, then they're totally fine. Okay, so no central control to report to. Okay, and self-organized or self-organized. So that means that if you were to leave them on their own, they can pretty much more or less function on their own. They don't have to collectively collaborate with others, and they can certainly act on their own if they wish, but probably wouldn't be as meaningful. Okay? So each agent operates, very non-intelligently, and they mostly act on instinct. So you just give it a basic set of rules, and that's what it does for the rest of its lifetime. Okay? So each agent operates on very simple, or you can call it non-intelligent behavior. Okay, so you can say that it's instinctual. Okay? So each agent, basically what's happening is that it can pretty much sense and move around their environment, and they also have the opportunity to interact with other agents as well. So they don't have to, they can certainly act on their own, but if there are people or if there are things around them, they can interact with them as well as other agents that are in the area. Okay? So each agent, perceives the environment, so they can sense the environment, and they can also change things around them as well. They can also change the environment too if they wish. Okay? So they can perceive the environment they're in, so, sensing the environment. And they can also change the environment as well, and can change the environment as well. So it depends on the scenario. Some people may not, some things may not change the environment, other things may. So each agent, so they can also change things around them, they can interact with the environment, and they can also share information with nearby agents as well. So it's a system that actually has memory. Okay, so it shares information with other nearby agents. So we usually can consider this as the system has memory. It can remember things, and it has a past history of things that it's done. Okay, so these non-intelligent agents together exhibit intelligent behavior. Okay, so something on its own isn't really saying much, but if you put them together and they work together and all that, they look like they do exhibit intelligent behavior. Okay, so that's pretty much swarm intelligence in a nutshell. So that's the basic definition. And what we're going to cover next is one such topic, which is particle swarm optimization. This part of machine learning and intelligent systems is cool because they make analogs to what happens in nature, and they try to put that in terms of machine learning terms, and they actually mix the two fields together quite well. Okay, so particle swarm optimization is the first topic we're going to cover. It's a population-based stochastic. What stochastic means is that it does updates one at a time. So it's a population-based stochastic optimization technique. Okay, so it is a population-based stochastic. So stochastic means that it does updates one at a time. Rather than waiting for everybody else to finish, they update as it goes. So, i.e. update after each, time step, I guess. Time step. Optimization technique. Okay. That's a bunch of gibberish, but let's keep going. So this is developed by two people actually, way back in the early, I believe, 60s or 70s or so. One of them was a social psychologist by the name of James Kennedy, and the other was an American electrical engineer by the name of Russell Eberhardt. Right, so developed by. So as a team of a social psychologist and an electrical engineer, which is actually a pretty cool pairing. Because you got someone that understands what's happening in nature, and the other one that'll take that and put it into actual physical terms that we can understand, in terms of us, us being engineers and all that. So you got James Kennedy, who's a social psychologist, and Russell Eberhardt. Who is an electrical engineer. Nice. So despite popular belief, people from different disciplines can work together. All right? So basically, the particle, sort of the whole basis behind it is that it uses randomized behavior to try to simulate swarm intelligence. So usually in nature and all, there's a bit of randomness that is associated with each agent, and we introduce randomness into particle swarm optimization to try to simulate swarm intelligence. I'll call particle swarm optimization PSO for short, because it's quite long to write out that whole that whole term. Okay, so uses randomness to incorporate swarm intelligence. Oopsie, I can't write today. To incorporate swarm intelligence into particle swarm optimization. Okay, so particle swarm optimization, what it's nice about it is that it's modeled after social behavior. So it's unlike genetic algorithms where you have the survival of the fittest, where you have some genes that are kept, some genes that are discarded, and there's mutations and crossovers. That's not done in particle swarm optimization. So everything is kept, and agents interact with each other in terms of the social aspect of things. So it's modeled after the, but social behaviors. Okay, this is unlike genetic algorithms, where where we perform such things as mutations and crossovers and elitism and all that. That's not done. Everything is kept the way it is. It's just different agents interact with each other in nice interactive ways. So mutations or survival of the fittest, none of that stuff. Crossover, etc. That's not done here. Okay? So the reason why it's called particle swarm optimization is because each agent would be a particle. Particle is the most abstract agent you can think of. But it's actually modeled based on bird flocking, but I'll talk about that soon. So each agent is a particle, which makes sense because it's called particle swarm optimization for a reason. Okay. So in particle swarm optimization, the basic premise is that you can think of particle swarm optimization as a swarm of animals trying to gather food somewhere. Okay? So they're scattered around some sort of search area, they're trying to find food, and if one particle or one animal will see that there's something promising, it's going to alert nearby particles or nearby animals to say, hey, there's something nearby here that we should go take a look at. So one particle alerts nearby particles, and those other particles alert nearby other particles, and eventually all of them will talk to each other, and they'll eventually converge onto the thing that they're after, whether it's a food source or something interesting. So what particle swarm optimization does is that it talks to nearby particles and eventually hones in on the resource or the food source that they're trying to acquire. Okay? So in particle swarm optimization, think of it as a swarm of animals. It's actually modeled after bird flocking, but in general, you can think of it as a swarm of animals searching for a food source. And I'll talk about how this applies to machine learning in a little bit, but I just want to give you a little basis on where this theory comes from. Okay? So what you do is you start by taking all these agents and randomly putting them in different places in the search area that you're trying to find the food source for. Right? So that's how you're going to start off. So, oopsie. So begin the search by randomly spreading out the swarm, in our case the particles, we're going to think of each individual instance, this is, as a particle, right, over the search area. Okay, and then let's see here. So each particle, when they're placed onto this particular search area, they've got an initial position and initial velocity. So there's position and velocity associated with each particle. So they have a particular position in the search area, and they have some sort of direction they're heading in before before things happen. So each particle, is placed in a different position, okay, and different velocity. So there's some speed that they're heading at, there's some direction that they're heading in at some sort of velocity. And we have, so this, the velocity means how fast they're moving. Just want to point that out just to be sure that there's no ambiguity. Okay, so each particle moves around the search area. So these particles are looking around, looking for a food source. And then as soon as one particle finds something that is remotely interesting or remotely promising, it's going to alert nearby particles to converge in on this interesting area, saying, hey, I've found something, let's go ahead and take a look, right? So if a particle has found anything good, it will alert nearby particles to converge onto the, onto the interesting area, I guess you can call it that. Okay? So in this case, what's interesting about this is that the particle has memory. It remembers a few things at each at each time point, and it's nice to know that it has memory. Okay, so once you start alerting other particles to converge onto this interesting area, eventually all of them are going to be alerted, and then you're going to converge onto this interesting area, and then you stop. Okay, so eventually, all particles converge in the interesting area, which hopefully would be your food source. Okay. Okay, so that's the basic premise of particle swarm optimization. So how does this apply to machine learning? How does this apply to machine learning? So what exactly about this applies to us? Why is this so special? Well, you can abstract each of these minute terms. So you can think of a particle as something machine learning, a swarm as something machine learning. So a particle would basically be a possible set of parameters that you'd use to put into your cost function to see if it's at a minimum. Okay? So a particle, in this case, would be a possible combination of parameters. Remember, in what we've seen so far is that you have to choose the right combination of parameters to get the best minimum for your cost function. Right? So one particle in this case would be some combination of parameters that we want to take a look at. So a possible combination of parameters. Okay? Then you can think of a swarm as a collection of all these particles together in some predefined domain. Okay? So it is a collection of particles. So we have a collection of all these possible combination of parameters, and one of them will hopefully lead us to the right solution. Okay? So it's a collection or a population of particles. Okay? In our case, the food source would be the minimum of the cost function. So the search area that we're looking at will be some surface of the cost function, and the food source would be the minimum of this cost function. So you want all these particles or all these sets of parameters to eventually converge down to where the minimum would be. And once we find that food source or that minimum, that's when we stop. Okay? So the food source would be the minimum of the cost function. which I'll call J, I suppose. Okay? And then the search area would be the list of all possible combinations that you could consider that would be defined for your cost function. Okay, so it's the set of all possible parameters. Okay, so usually the search area is going to be quite large. So you usually try to restrict it within a certain range, like maybe within a box within a grid or something, but usually the search area is very large. So you want to confine it down to a subset of the search area before you start the algorithm. Okay, so sometimes this is very large. Okay, so restrictions are usually imposed on the search area. Okay, so you restrict while you're searching. Usually the search area is quite large. Okay, so that's all nice in theory and all that. So let's actually show a graphical example. Here's a nice example that I pulled off from a guy's website. Actually, it actually illustrates particle swarm optimization in a nutshell quite well. The source of this was a guy named Jonathan Becker. Okay, so here's a graphical example. So each of these pink dots would be determined. You could think of this as one particular particle or one instance of the cost function, or the one instance of those parameters that you're trying to solve. And each of these particles have some sort of velocity or some sort of direction they're heading in. Okay, so then what's going to happen is that you have these particles here that are going to notify, perhaps these neighboring agents, and then these neighboring agents are going to notify these guys, and it keeps doing this, and it keeps doing that. What happens is that as the neighboring particles notify each other, they're going to all eventually converge towards the food source, which is labeled as the blue star. So at the very beginning, it's all random, and then when they all talk to each other, in the end, they'll finally converge to pretty much around where the food source is, and that's where we stop. Okay, so the blue star is the food source. In this case, this is the desired minimum of the cost function that we seek. Okay, so it's the minimum of the cost function. Okay, so then each particle is a potential solution, or each particle is one possible set of parameters that we would like to see whether or not it's the minimum of a cost function. So each particle is a potential solution. And this is defined in feature space. So in this case, we've only got like two parameters. So we've got theta 0, theta 1, and this is the cost. Okay, I just want to put that in. So in this case, this is just two features for now, but this can apply to pretty much n features. But I did two here, or not did, but I showed two here just to make a graphical example that we can picture. Okay, so each particle is a potential solution, and it has a velocity, and it has some direction that it's heading in. So when you alert the other particles, what you want to do is you want to change that direction so that it converges into the interesting area that the other particles are interested in. Right, so it has some direction. It is heading in. Okay. So initially, initially, all particles are randomly placed. So they have some sort, they're randomly placed around the search area, so they're trying to find a food source. So they're randomly placed, okay, with, random positions and velocities. Okay, and then eventually, so this is what we want to look at. So eventually, all particles converge to the minimum. Food source, and we stop. Okay, so it's going to oscillate, more or less around the food source. So you have to figure out some criteria to make it stop. Either, the particles don't really move that much between successive iterations, or if the cost function is less than some desired value, but there are multiple things that you can check, and we'll talk about those later. Okay. Okay, so with particle swarm optimization, as I talked about, each particle has memory. So for every particle that is in your current system, it remembers 4 things. So each particle remembers 4 things, and this information is shared with other particles to try to converge to the actual minimum of the cost function. So each particle has 4 things to remember. Okay, so these 4 things we have to remember. So the first thing that we have to remember is the current position, which I'll call x sub I, right? Because what's happening here is that this is an evolving algorithm, so there's time steps, time step 0, time step 1. So x sub I would be the position at time step I, okay? So so in terms of the position, what you see here is these particles are spaced in feature space. So the position of the particle, the location of the particle would actually be a set of parameters that are unique to that particular position of that particle. So current position would be the parameters represented by this particle at time step I. Okay, so as you see here, there's time step 0, which is the initialization step, and then we keep incrementing the time steps until, something, converges. Okay, so the current position, we also have the current velocity. So each particle has a position and an associated velocity, which we'll call v sub I. And what this does is that it tells you how much the particle needs to move in a particular direction so that it can update itself and check to see whether or not that new position represents the minimum. Okay, so this is how much we need to update xi for the next time step. Okay? The next one is what's known as the best position this particle has seen so far. Okay, so when the particle, when it swarms around or when it looks around the solution space or this cost surface, it also remembers the best cost function value that it it has seen so far. So what you're doing is, as you're updating the position, what you want to do is you want to check to see whether or not the updated value is better than the one that you remember. And if it's better, then what you're going to do is you're going to remember those set of parameters that give you the lower cost function than what you've seen before. Okay? So this is the best position this particle has seen so far. And in literature, it's commonly known as P best I. So the best position at time step I. Okay? So from time step 0 up to time step I, which position gave the lowest cost? So that's what we want to remember. So out of all the positions we've seen so far as it's updating, as it's moving around the search space, what is the best position that we have seen so far that has provided us the lowest cost so far? Okay, so that's what's known as P best I. It's the best position for the ith time step. And then finally, we have what's known as the neighboring best. So remember, particles like to talk with each other. So you have the best position that that particular particle has seen so far, and then you also remember the best position that the neighbors have seen so far. So that's how we actually collaborate, and that's how all of the particles will eventually converge to a solution. So you have not only the best position that the one particle has seen, you also remember the best position the neighboring particles have seen as well. And then you'll want to be able to converge to where the neighbors are going. All right? So we also remember the best position this particle's neighbors. So that's the most important thing about this is you have to talk with other particles in order to figure out where exactly you want to go. Right? So you also have this particle's neighbors has seen so far. And we call this term G best I. All right? So from time step 0 up to time step I, okay, which position, of this particle's neighbors is the best seen so far. Gave the lowest cost. So those are the four things to remember. So the current position or the current state of parameters that particle embodies, the current velocity or the current direction or the current updates the update vector that you're using to update the positions. And then you also have the best position that particle remembers and the best position that the neighboring particles that surround the particular particle you're looking at remembers. So those are the four things that each particle remembers as you evolve the algorithm. Okay? So, I'm actually almost done here. Good. Okay, so I'm actually almost done particle swarm. So once I lay out the algorithm, we'll take a break. Okay, so once we find the best position that the particle remembers at that particular point in time, and the best position that the neighbors of that particle remember at one time. Okay, so once we find these, then what you're going to do is we're going to provide an update. So we're going to update the position and update the velocity to converge on the interesting area that the neighboring particles have seen. Okay, so for a given particle, okay, we update the velocity and position for the next time step. So you're going to use this information, these four pieces of information, for that particular particle to update and move towards the area of interest that all the other neighboring particles are talking about. Okay, so we want to update the velocity. So going to the next time step for the velocity, it's a combination of three terms. So you've got some constant C0, and then VI, right? So this is the current velocity of that particular particle. And then you're going to have another constant, and then we have a random value, which I'll call U01. So this here is just a uniform random variable between 0 and 1. So it's basically just a random number that you choose between 0 and 1. 1 is exclusive. So it's what's called a uniform random value. In this case, it fluctuates between 0 and 1 exclusive. And in MATLAB or in C or any programming language that you use, this is called the rand function. Okay? And then you have so you have this term, and I'm going to explain what each of these mean very soon. I just want to write this out, and then I'll explain each term as I go. Okay? This is also a uniform random value as well. Okay? So all right. So so we have these terms. So the first term is very simple. Okay, this term, what it does is that it makes sure that the particle keeps going in the direction that it is, and then you'll allow the other two terms to make some adjustments. So this allows the particle to keep moving, right? So this allows particle to keep moving. And this term C0 we like to call the learning rate, if you remember, from stochastic, from gradient descent and all that. So this controls how much of a contribution that particular, velocity from the previous time step affects the actual update for the current time step. Okay, so this is a learning rate. This is also a learning rate. Okay, and this is a learning rate too. So these constants you'll have to define beforehand, and I'll talk about possible constants you can choose that will work. Okay, so I've talked about these. This allows the particle to keep moving, and then I have this particular term here. And what this does is that it's basically an attraction term. So what this is doing is that for the best position that we've seen so far, if we venture away from the best position, this will be an attraction term to make sure that it goes back to where the best minimum that the particle has seen so far to go back. So if we verge away, this term will make sure that we actually move back to where we're supposed to go. All right? So this is what's known as an attraction term. So this is an attraction term to move towards the best solution. Best solution particle I has, this particle has seen so far. Okay, so that's that term. This term here, what it does is that it's an attraction term that makes sure that the particle moves to the minimum that the neighbors have seen. Okay, so this is an attraction term to move particle towards the best solution the neighbors have seen. So these two, have seen. So these two terms work side by side each other. So eventually, when one particle actually meets the minimum, both of those terms will eventually be small, and then it'll actually start to converge. So common term actually. So this is. So we've got one more on here. So we've got that. So common constants are. Usually we set C0 to 1, and then you can try, C1 and C2 equal to 2, right? Usually you try between 0 and 4, exclusive. So usually it's between 0 and 4. That's what's seen in practice. Okay, so what this is doing here is each of these terms, so you have P best I and Xi, each of those terms are n-dimensional, where n is the total number of features that you have. So these are all vectors of length n, where each element is a feature, a particular feature, or an update to the feature that you're looking at. Okay, so each of, so P best, G best, let's see here, Xi and Vi are n-dimensional. Okay, where n is the number of features. Okay. All right, so this would be the velocity update that we would need to update the position. So once you have that, all you do now is you just update the position for the next step, which is the previous plus, plus the actual update here. Okay, so what this is doing is that we are updating the position for the next step. Okay, and this here was from equation 1. So what you do is you calculate the velocity first, and then you use that to update the position so that you're making the parameters move towards the, something that's interesting, or the global minimum, whatever that may be. Okay? All right. So there's one last point I'd like to point out. So in practice, sometimes what we'd usually do is that the velocities can vary very wildly. The dynamic range can vary. So what people usually do is, if you calculate the velocity of a particular component, if it goes beyond a certain threshold, then you cap it at that threshold. So for example, let's say the velocity was like 2.6, and the cap would be 1.5. So if anything was beyond like negative 1.5 to 1.5, you cap it at 1.5. So you restrict the velocity because the dynamic range is very heavy. So it also prevents oscillating around the actual minimum. So if you restrict the largest velocity that particular update can make, then it will minimize how much you oscillate around the actual minimum. Okay, so in practice, the velocities, EI, are also clamped to a maximum velocity. Which I'll call Vmax. And, oopsie, this should be block. Okay, so what I mean by this is if Vi plus 1 is greater than Vmax, okay, then you just cap it at Vmax. For each feature, I guess. So you do it component-wise. Okay. All right, so the last thing I haven't talked about is defining a particle's neighbor. So we have one particular particle, and we have to, there are neighboring particles that surround that particular particle of interest. But I haven't defined what actually are neighbors, right? So there are different definitions of neighbors that you see in practice. One would be to consider, you have a particle and then perhaps maybe a sphere or a radius around the particular particle you're looking at. That would be considered neighbors. Or one would be to choose particles at random. So you have one particular particle and then you just choose a bunch of neighbors at random. That would be considered neighbors. And then one other possible scenario will be to make everything neighbors. So there's three different scenarios you can choose, and it depends on what exactly the problem you're going to solve. But we haven't defined that. So defining a particle's parameters, not parameters, neighbors, sorry, is up to you. Okay? Some common definitions are okay. One would be to choose all particles as neighbors. So if you have 10 particles in your system, you have one particular part you're looking at, you consider everything to be neighbors, which, there are ramifications for that, and it depends on what you're trying to do, and it just depends on experimentation to figure out which one you want. So choose all particles. The next one, sorry, gonna go down. The next possible scenario will be to choose within some radius of the particle. So in the case of what we have for the two features, it's basically traversing in 3D space. So for a particular particle, you take a look at perhaps a sphere of radius 2 or 3 or whatever radius you're looking at that's around the particular particle at the first time step, and then you'd consider those to be the neighbors of that particular particle. Okay? Choose within some radius of the particle at iteration 0, or the initial point. Okay? And last but not least, you can just choose k particles at random. So there's no predisposition on what particles to choose. You just have one particle and you just choose k random particles that are unique and say, hey, those are my neighbors, and there you go. Yes?
So for step 2, does that mean that halfway through the iteration, the neighbors won't change?
Yeah, the neighbors don't, so the neighbors actually, yeah, so with let's see here. So yeah, so what you're doing here is you initialize the neighbors first and you don't change them as the algorithm changes. So for number 2, at time iteration 0, you say, okay, these are the neighbors I'm looking at, and then those don't change. And then you just iterate through the algorithm. So the neighbors don't change as the algorithm evolves. You choose the neighbors, and then that's it. It stays static for the entire algorithm. Okay? So I like to point that out. That's very good. So neighbors don't change after initialization. Okay? So I'd like to point that out. Thank you. That's a very good point. All right, so I'm just going to lay out the algorithm here, and then we're going to take a break. So I'm actually pretty much done on this particle swarm stuff. Okay, so here's the particle swarm algorithm in its, fame and glory. Okay? So the first thing you have to do is there's a bunch of initialization that we have to do. So the first thing you have to do is figure out which parameters you want. So you got to figure out the learning rate, C0, C1, C2, figure out the maximum velocity cap, Vmax. You also want to figure out the number of particles you want, right? That's pretty important. And then you have to choose a bunch of parameters. So figure out the neighbors you want to choose, initialize everything. So there's a bunch of steps that you have to do before you actually start doing the algorithm here. So yes?
If we choose random particles, don't we have to be worried about whether or not they end up forming separate clusters?
Mm-hmm. So what you do is with that case, when you're choosing random, what you do is you repeat the algorithm a certain number of times, and then you choose the configuration that gives you the best cost. So so the random stuff is seldomly used, and if you do decide to do that, then you have to run the algorithm a few times to make sure that, to make sure that the minimum that you get is repeatable. Okay, so 1 and 2 are usually stable. 3 people like to choose if they can't visualize the data. And if you choose the third definition, then you have to run the algorithm several times to make sure that the minimum is stable. So that's a very good question as well. Okay? So it's almost like that k-means stuff where you have to run k-means a few times in order to converge to the actual true minimum. So it's the same case over here. Okay? So initialization. So we provide, the constants, right? So the learning rates plus the cap max, okay? You also want to provide the number of particles. which I'll call n, okay, capital N. Okay? You also, what you do is you provide random positions, xi for all particles. So you're going to initialize the positions to be random because you want to scatter them across the search space. You also want to initialize the velocities too. Actually, let's call this 0. The reason I want to initialize this, right? So initial velocities. Okay, and okay, so you've got that, and then restrict search space if desired. So that you want to define beforehand, okay? And then what you want to do is you want to initialize 2 things. So what I'm going to do is define f p best I. Okay, so this will be the actual cost. That is defined for p best I, okay? So, the p best I, what that is that it is the position that is the smallest that the actual particle has seen so far. And with that position, there's an associated cost. So we also not only remember the position, we also have to remember the actual cost associated with the actual position, so which I call f p best, okay? So we also define f g best, which is the cost that is associated with the best position the neighbors have seen so far. So this is the actual cost that is defined for G best. Okay? All right, so so those are a bunch of initializations, so we have all that, okay? Now what we're going to do is the actual algorithm itself. So we're going to repeat until convergence. So here's the main algorithm, right? So it's nice to actually see the step-by-step process, and then you can kind of put the theory to a nice list of steps. Okay, so what you're going to do is for each particle, this is the first step. What you want to do first is you want to find p best I for all particles. So what we want to do first is we want to, for each particle that we have, we want to determine what the best search position is so far. Okay, so for each particle, what you want to do is calculate cost function. So the cost defined for these particular parameters, xi, okay? And then what you want to do is you want to check to see if this cost function value for these particular parameters is less than the best value for the cost function we've seen so far for this particular position. Then what you're going to do is you're going to replace this best cost function value with the cost that we've seen, and then we also update the p best so that we remember this particular position. So f p best I is equal to this new cost value, and we also update the position as well. So what this is saying here is record best cost and particle position seen so far. So we want to figure out, what the p best I is. So remember, when you're doing that update, you have to figure out 2 things. You have to figure out what the best position is for that particle, the best position for the neighboring particles, and then we finally do the update. So this is the first step. And then the next step you want to do is you want to find the best position for the neighbors. So for each particle, right? So you want to find G best I, right, for all particles. Okay, so what we want to do here is find the smallest cost over all neighbors of the particle. Okay, so what you want to do is you want to find the smallest cost over all the neighbors of that particle seen so far. So what you basically do is you take a look at the neighboring particles and you take a look at all of their P best values, the cost value for all the P best values, and then you set G best to be the minimum of all of these best cost values. Okay, so what you're doing is search over all P best, or the cost of the best for all neighbors. Okay, so we're gonna call this, so call this cost C, and the position, we'll call it C sub I guess. Okay, so the cost of this particular neighbor that is the best, and the associated position we're gonna call CI. Okay, so then what you're gonna do now is you're gonna check to see if this cost is currently better than the cost of the neighbors that you've seen so far. Then you're going to update everything. So you'll get F G best I is equal to C, and then finally you want to update the position to represent these new values. Okay, so in this case here is record best neighboring cost for particle and position so far. Okay, so you've got that. So that's the G best step. Okay, and then what you're going to do next is you're going to update the positions and the velocity. So that's the last step. So for each particle, so what we're going to do is we're going to update. This is the last step, and then I'm going to take a break. So the update positions and velocities. Okay, so what you're going to do now is you're going to do this stuff that we did before. So this is C0 VI plus C1. Let's see here, the random value, and then P best. Okay, and then you have this one too. This is G best. Okay, and also you want to make sure you cap the maximum. So if this right now is larger than the max, then you cap it at the max. So do for each feature. So what you do is you look at each element in this velocity vector, you check to see if it exceeds a certain maximum, and if it does, you set that to the maximum for each of the features themselves. Okay, so you have that, and then finally you update the position. And we finish, and we finish, we're done. So you have those two steps. Update the P best, update the G best, and then update the positions and the velocities. So the last step would be convergence. So we converge if we exceed maximum number of iterations. So sometimes, the particles may swarm around the minimum, but they may not converge. So you want to cap the number of iterations. Or if the cost of the best position for all the neighbors seen so far, so G best, if one of, is less than some threshold, epsilon. Call this a threshold. So you either stop if we exceed the maximum number of iterations, or if one of the best neighboring cost values that we have seen, is less than some threshold. And then once you find that particular one, you stop, and then you output the one that produces the best. Okay, and that's it for particle swarm. So we'll take a break, and then we'll come back and cover the next one, which is ant colony optimization.